to omit almost all of the notes. There's just too much material in the notes, and if we want to get anywhere, it's best to be left out. And I'm going to concentrate on the proof of Fermat for n equals 3. That's basically Kummer's proof, and I think was probably devised after Kummer. Now, there are two things to be done with this proof. You have to, assuming unique factorization, that we'll explain, you have to prove the theorem. I found the book, by the way. It's in the library. Then one has to prove unique factorization. Now, this is, so to speak, the most difficult mathematics that we'll have to do. So I had thought I would do one of those things this week and one next week. I suspect that we may have to do them both. We may be able to do them both this week, which might even give us a week free. But I think it would be a good idea, since it is the most difficult mathematical part, that no one hesitate to ask questions. Right? That would be the time to ask questions, I suspect. And it won't be so difficult for the mathematicians, but for those, one has to indulge in a real proof, I think. And there are some calculations and so on that in which I could very easily lose you. And so if you're lost, say something. It would probably be better to take 2 hours than just one. All right? So this is now it's out of sequence. So we never discussed Euler's proof. So we never discussed, we just indicated briefly last time what was missing. Maybe you've looked at the notes. If you have, you'll have seen what was missing. And
over here.
Huh.
Could you make it more in focus for us?
It can't be uniformly in focus. That's the difficulty. It may be better. Huh? That's enough? Okay. If you have the notes, you can follow it in the notes. So, okay. There are two sides. All right. So, there's an element, and what's okay. Those are the old notes. Right? No, there are no new notes. Huh? So most people have copies. Maybe not everyone, but no. It's that you last time you may not have got.
Oh, thank you. I have it in my office. I'll use it and return it.
Okay, good. Thanks. People at the Institute, to my surprise, are not very ecologically minded. I'm glad to see. They all waste their gasoline driving from the project to Fultala and back again. Don't set a very good example to the rest of the population. But. So there's an element in Euler's proof, if we had done it, that was missing. And here it's the statement of unique factorization in this domain, which we consider. Alpha is the cube root of unity. So the statement is that every number was a product of this form, where epsilon is one of those 6 units, and pi 1 and pi 2 and so on are different primes. So they're essentially different in the sense that one is not obtained from the other by multiplication with a unit. And what we'll have to show is, first of all, that this is possible, and secondly, that the factorization is basically unique in the sense that if we had a different factorization of the same number, then what we might do is replace pi 1 by unit times pi 1 and epsilon by some other unit, or pi 2 by unit times pi 2, which wouldn't change the nature of the factorization, and epsilon by some other unit. So here's an example, just so it's clear. So suppose that this was the number c, which was minus 80 plus 19 alpha. And we saw that 1 plus 9 alpha and 3 plus 11 alpha were primes. That was earlier in the notes. So then this c is 1 plus 9 alpha times 3 plus 11 alpha with any luck. You have to multiply it out and use the fact that alpha squared is minus alpha minus 1. And what this is equal to, it's equal to, so that's one way of writing it, is pi 1 times pi 2. That would be pi 1, that would be pi 2. And we could also multiply this number by a unit. For example, we could multiply 1 plus 9 alpha by alpha, which would give us minus 9 minus 8 alpha, which would be that. And we could multiply this by a unit times maybe minus 1, which would make it that. And then we'd have to introduce a new factor in front to make sure they're equal, and that would be minus alpha squared, which is again a unit. So there's this ambiguity with which one has to deal, and it's just a nuisance. All right? So what we're going to do is take this unique factorization for granted and prove that there is no solution of x cubed plus y cubed equals z cubed for integers, unless one of them is 0, in which case it's easy. X cubed is equal to x cubed with y equals 0. So, and it's slightly, sometimes it happens in mathematics that it's convenient to prove a stronger statement. And the stronger statement is to prove, so x cubed plus y cubed equals so, I mean, if we had something like x cubed plus y cubed equals z cubed, well, that's the same as x cubed plus y cubed plus just replacing z by minus z is equal to 0. So what we're claiming is that this equation has no solution unless one of those three numbers is 0, and we're going to prove something slightly stronger, namely that even if we allow numbers from the domain, so C would involve alpha and eta, and zeta would also involve alpha, then this is not possible. So we prove the stronger statement. This is sometimes that's the way you have to go. So let's do it. So what we have to do, it's a rather grueling task. We have to prove 4 statements, of which this is the first. And in order to make the statement, I use a modern notation. So I write this equals with 3 bars to mean that the difference between the two sides is divisible by this third number here. So this means that C minus eta is a multiple of zeta. All right? So I recall 2 things that we'll need, that this lambda we introduced, 1 minus alpha, was a very unusual prime, and it plays a particular role in the proof, and that 3, if I take the unique factorization of 3 that exists over there, then the pi, there's only 1 pi 1 in its lambda, and it occurs to the second power. So that's what we need to know. That we had. Huh? Yes.
When you say modulo zeta, you say a multiple. You mean a multiple by an element of z alpha or a multiple by an integer?
Yes, thank you very much. I mean a multiple of an element in z alpha. All right. So this means that C minus zeta is equal to mu times zeta, where mu is an element of z of alpha. So it's one of these numbers, a plus b alpha. Thank you. So statement 1 is simple, but so it says that if omega is not divisible by lambda, no, then omega cubed is common minus either plus 1 or minus 1. You have to change your notes, is divisible by lambda to the 4th. So this is the first thing, and so this is a tedious argument. I mean, but one has to be clever enough to get it in there where it's needed. So here's omega. It's one of our numbers. It's a plus b alpha. So I want to say omega cubed is equal to plus or minus 1 plus the power of lambda. So omega plus b, if I replace omega by omega plus b lambda and expand, then I'm going to have a lot of lambdas in there, but I'm not going to change what the residue modulo lambda. So if I had omega plus lambda all cubed, that would be equal to omega cubed, if you expand it out, plus 3 omega squared lambda, plus 3 omega lambda squared, plus lambda cubed. So that part involved is a multiple of lambda. That part's a multiple of lambda. And so is this. So it only leaves that. That means as far as this statement goes, I can replace omega by something times, I can add something times lambda to it. So I might as well add something times lambda to it to make my life easy. So I add omega plus b lambda. Maybe, let's see, it's b alpha plus b. Lambda is 1 minus alpha, so b lambda is b minus b alpha. I put it in here, and I just get a plus b. So I might as well assume, making this statement, that omega is just an ordinary integer. Now 3 is a multiple of lambda, we saw that. So if I add to omega any multiple of 3, it's also a multiple of lambda. So since any integer is either 0 plus a multiple of 3, or plus 1 or minus 1 plus a multiple of 3, in other words, if I have 5, it's equal to 2 times 3 minus 1. 7 is 2 times 3 plus 1, and so on. So I might as well really simplify life and get down to omega being one of those 3 numbers. All right, so as I say, if I turn around, you can ask a question. You should ask a question, otherwise we'll race right through. So 0 is excluded because omega is not to be divisible by lambda, and that means it's plus or minus 1. So here's what we have to show. So we just have we could actually okay. I'm sorry. Somebody should have asked a question, and somebody should have objected, right? I cannot, I mean, all I have said is that any number omega, I was actually saying I could replace omega by a plus b. I cannot replace omega by a plus b. All I can say, all I've done is say that any omega is congruent to one of these 3 numbers, is equal to one of these 3 numbers plus a multiple of lambda. Right? I was trying to say more. I was trying to say I might as well assume it's 0 or plus or minus 1. This I'd better not do. All I know is that it's equal to one of these 3 numbers plus a multiple of lambda. So it's of this form. That's all this argument shows. Now, then omega cubed minus 1. Now let me go ahead, because let me just do something a little bit. I think okay. I should have done something beforehand. Let me jump ahead here. If you don't believe this, you may believe this right away. That omega cubed minus 1, we've seen this. We know that the 3 roots of z cubed minus 1 are 1 alpha and alpha squared. So we know this relation, or if we want, we can jump ahead in the notes and take the particular case that c is omega and that eta is minus 1. So this is omega cubed minus 1, and we'll check this later. We have this expression, and we check it just by multiplying this out. This would be omega minus 1, omega minus alpha, and omega minus alpha squared. So if you want to check this relation, you can jump a couple of pages ahead and see that it's a special case of that. In any case, that's it. And there's omega. It's 1 plus beta lambda. So here we have omega minus 1 is beta lambda. Then we have beta lambda plus 1 minus alpha. That's omega minus alpha. And 1 minus alpha is lambda. So this is beta lambda plus beta. This beta lambda plus lambda, which is pulling out the lambda. I get lambda times beta plus 1. So from here I get beta lambda. From this part I get a lambda that I put here, and I'm left with beta plus 1. And here I have beta lambda plus 1 minus alpha squared. And we have to go back and recall that indeed minus alpha squared, so we're over there, we have 1 minus alpha squared, and we have to go back here and recall that this number here is alpha squared minus, is alpha squared, we did it before, times lambda. You can easily check it, but this is alpha squared. So this number, 1 minus alpha squared, is nothing but minus alpha squared times lambda. So we have a lambda here, minus alpha squared times lambda, and we pull out another lambda. So we get that. So here we are. What are we saying? We said we might as well, multiplying omega by minus 1 if necessary, which just puts a minus, changes the sign on this side. We might as well suppose that omega is congruent to 1, because it couldn't be congruent to 0, not divisible by lambda. And then we have this equals that. And we've got 3 omega cubed minus 1 being divisible by 3 powers of lambda. And the claim is it's divisible by 4. So in the special case that omega is congruent to 1 modulo lambda is this form, we have a plus 1 on this side. So we just have to make sure that beta or beta plus 1 or beta minus alpha squared, that one of these 3 numbers is divisible by lambda, and then we get our 4th power. Now alpha squared is equal to alpha squared minus 1 plus 1, that's clear. And this number is a multiple of lambda, that's one of the numbers here, alpha squared minus 1. And so what we get is, apart from multiple of lambda, we have 1. So alpha squared is 1. That means as far as multiples of lambda are concerned, in this times this times this, and therefore as far as multiples of lambda fourth are concerned in the whole thing, we might as well replace minus alpha squared by minus 1. So we get beta times beta plus 1, beta minus 1. And since we have 3 powers of lambda here, we just need 1 more. And we've just seen that any number is either a multiple of lambda plus 0, plus 1, or plus minus 1. If it's plus 0, it's a multiple of lambda. If it's a multiple of lambda plus 1, then this is a multiple of lambda. A multiple of lambda minus 1, then this is a multiple of lambda. Okay, that's statement number 1. Questions, answers, criticisms, anything? It's okay, no. There could be, we can come back. All right, so this argument is built up of 2 simple but apparently pointless calculations, which this is the first one, right? And we're going to give a second one, and then we come to the argument itself. So, statement number 2. Guys, as I said, this I think is some of the hardest work we have to do in the course of these 15 to 16 lectures. So the statement 2, remember we're trying to show this is impossible. And what we claim is that if it's, so we have first to see what it means. And what it means that one of these 3 numbers is divisible by lambda. That's the claim. Now, what do we know? We know that if neither of these numbers is divisible by lambda, well, we apply this statement to each of them. Then each of them, the cube power of each of them is congruent, is plus or minus 1 modulo lambda to the 4th. That means up to a multiple of lambda to the 4th, each of those numbers is plus or minus 1. So what do we get? So if this is equal to 0, then this is equal to plus or minus 1 up to a multiple of lambda to the 4th. So is that, and so is that. So the sum is equal to this up to a multiple of lambda to the 4th. Now we're going to sum 3 numbers, each of which is plus 1 or minus 1. Well, either 2 have opposite signs and cancel, in which case we're left with the third, and we get plus or minus 1 is divisible by lambda to the 4th. Now that's clearly impossible, plus or minus lambda, because lambda is not a unit, so it's not going to divide plus or minus 1. So that's out. Otherwise, they all have the same sign, in which case they pile up, and we have plus or minus 3 is congruent to 0 modulo lambda to the 4th. That means in the prime factorization of this particular prime occurs at least to the 4th power. But we know, we actually worked that out before, that it only occurs to the 2nd power. So that's out of the question too. So we suppose that none of these was divisible by lambda, and we arrived at a contradiction using that. So one of those numbers is divisible by lambda. Since they appear in a perfectly symmetric way, we might as well call that one zeta. So here's zeta. It's a multiple, some multiple of lambda. So it's lambda times something times a number which is not divisible by gamma. Notice we're just working with these numbers the way we'd work with ordinary numbers, the way we'd say, for example, that 20 is 2 squared times 5, right? Or 36 was 2 squared times 9, or 48 was 2 to the 4th times 3, or something like that. We're using that. So we're really using this unique factorization that we haven't proved yet strongly. So now we have this. We put this in, and we want to prove, since zeta is of this form, now we want to prove the impossibility of this, in which we now have a power of lambda out there. So we've changed the equation a little bit by replacing zeta by gamma, and we have an nth power of lambda. Now, if zeta is divisible by lambda, then we couldn't have and eta were divisible by lambda, then this part would have to also be divisible by lambda. So that's out of the question. So once zeta is divisible by lambda, the other two are not. So these two are not divisible by lambda. And although we didn't say it, we could have said it at the very beginning. Or I should have said it at the very beginning. It's in the notes. Namely, what I should have said, that if those three numbers were divisible, all divisible by some prime, I just divide that equation by that prime cube. So I might as well assume that they're not all divisible by the same prime, and therefore that no two of them is divisible by any prime. So they all have different divisors. We're using this unique factorization very strongly. So there it is. We want to show that's impossible. And once again, we make a slightly stronger statement. We prove that even this equation is impossible with a unit epsilon there. All right? Now look at the argument. Now the argument, after these two initial calculations, is it okay. Thank you. Oops. All right. So we're going. So this statement, which is a calculation, this statement was a calculation. Now we have an argument with the structure. And look at the structure. We proved two things. We show that if this is possible, then this number n has to be larger than 1. On the other hand, we show that if it's possible for a given number m larger than 1, then it's also possible if we have a number 1 smaller. So for example, if it were possible for 3, then by this it's possible by 2. And then applying this again, it's possible for 2, it's possible for 1, but we know it's impossible for 1. All right, that's the argument. So that would be called descent argument. So this is the. So let's just look at this. So remember, all three of these, none of these numbers is divisible by by lambda. So I can't say, well, bring that lambda and make it part of gamma and make n smaller. No, that's hard. It's harder than that. So the first of these statements is easy to verify, statement 3. So when I say it means, I mean it implies that. If B implies that this number is equal to, or minus this number if you prefer, is equal to c cubed plus eta cubed. So this number, and we use the statement 1 again, c cubed is plus or minus 1 modulo lambda to the fourth. Eta cubed is plus or minus 1 up to a multiple of lambda to the fourth. The signs cannot be the same because then we would have 2 here. And whatever the number is on this right-hand side, so we have these two numbers are the same up to some multiple of lambda to the fourth. So if, for example, we had 2 here, then we'd have some multiple of lambda to 3n is equal to 2 plus some multiple of lambda to the fourth. And this is at least lambda to the cube. This is at least lambda to the fourth. So 2 would have to be divisible by lambda to the cube. But we know that lambda doesn't divide 2 at all. 2 is a prime. We checked that too. So we have a lot of incidental information that we use about this domain. So as though we really were proficient in multiplying in this domain. So we can't have plus 1 and plus 1. We can't have 2 here. For the same reason, we can't have minus 2. That means we have opposite signs. So this part is 0. So this left-hand side is divisible by lambda to the fourth. But there are no multiples of lambda inside gamma. So all the multiples of lambda are inside lambda to the 3n. And we can't have 4 of them if we have lambda cubed. So we're going to have so we can't have n equal 1 because then we just have lambda cubed being a multiple of lambda to the fourth. So n is at least 2. So there we go. So now we come to what is the heart of the argument to prove this. So this is what is called.
Is there a misprint evaluation of the gamma to the power 3 in those two equations? It doesn't matter.
Here?
In that equation and the previous one.
Well, I'm verifying a consequence of this, and what I'm saying is that this consequence will not be valid unless n is bigger than 1.
I think he's asking for the misprint and gamma to the n. Is the gamma to the third?
Oh, excuse me. Yes. Yes, thank you. Yeah, thank you. So all right, so all right. So it's the last statement that we have to work at. So the last statement, so this descent is the part that goes back to Fermat. This, and as I point out, until very recently, it was the most powerful method for dealing with such questions. So what we're going to show, so as to say, is that if this is possible for 1n, it's possible for 1 smaller and smaller and smaller until we get back to a statement that's contradicted by statement 3. So we have to do some more of these fastidious calculations. All right. So we begin by, we have this relation, and we factor this c cubed plus eta cubed in this way. Now I checked this. This is, so to speak, a familiar formula to lots of people, but just so that we could be sure about it, you just write it out. You just expand this out. You get c cubed, for example, and then you get c squared eta, taking 2 c's and an eta, and you can get 2 c's and an eta with alpha squared, 2 c's and an eta with alpha, two x's and an eta alone. So that's this part. The same way you get this, in which you just take one xi and two etas, and you look at what coefficients you get. And finally, eta times alpha squared eta, we get alpha cubed, and that's 1. So this is just eta cubed. So that works out. All right. Now we have to look carefully at this. So we have C, and we have these three numbers. And we look at the difference between, say, the first and the second. We take the difference between the first and the second that I should have done here. So I take C plus eta minus C plus alpha eta. No. Okay, so this would be C plus alpha eta. Then the x's cancel. I'm left with eta minus eta alpha, which is eta, times 1 minus alpha, which is lambda. So the difference between this one and this one is eta lambda. I should, if with any luck, the difference between this one and this one, the x's go away, and I'm left with eta minus alpha squared eta, which is pretty much alpha, which will again be a multiple of lambda. So it'll be lambda times a unit, and the third difference is again lambda times eta, and then there's a unit involved again. So each of those differences is divisible by lambda, but none of those numbers is divisible by lambda squared, because alpha and alpha squared are units, and eta is not divisible by lambda. Now think of it. In other words, what does that mean? You see, their product is divisible by lambda to the 3m, and this is at least lambda, working with statement 4, at least lambda to the 6th. So we have three numbers which are divisible by the 6th power of a prime. That means at least one of them is divisible by that prime because of unique factorization. But the difference between any two of them is again divisible by that prime. So for example, it's like saying I have product of three numbers which is divisible by, say, 2 to the 6th. Any luck, that's 64. So the difference between each of them is even. What does that mean? Well, I'm sorry. Okay, that means that one of them, no two of them can be divisible, say, by 4, because then the difference would be divisible by 4. So no two can be divisible by 4. One of them has to be even, and they all would have to be even because their difference is even. So if we were at lambda, we're 2. So they're all divisible by lambda, but they're not divisible by lambda squared. So that means one of them has to bear the full burden for this. So one of them is divisible by lambda to the 3m minus 2, and then each of the others is divisible by lambda. So in order for this to work out, one of these is divisible by lambda to 3m minus 2, and the other two are divisible by lambda. No, we couldn't have two of them being divisible by lambda to the square, but they're all divisible by lambda. Now, since we can replace eta by alpha squared eta, because this alpha cubed is 1, alpha squared cubed is 1, that means that this number in this solution is not uniquely determined. If we replace eta by alpha eta, we don't change this equation. So we might as well, since one of these is divisible by lambda to the 3m minus 2, and since they all play equivalent roles, we could have replaced eta cubed by alpha eta cubed, we might as well assume that this one, right? This is the one that's divisible by at least by lambda squared, in fact at least by lambda to the 4th it will be if m is 2. All right, so I'll be coming along all right?
I don't understand the argument about the differences, because that proves that one is that each is divisible by lambda, but not by lambda squared. That's what the figure is trying to prove.
Okay, so
The differences between each pair.
these are the differences, right?
I understand what they are, but I don't
All right. Well, no, I just wanted to make sure where we are. But eta is not divisible by lambda because all right, it was zeta with alpha, with xi eta. So the only way, I mean, we want to see, we have a number which is not divisible by lambda times lambda, so that's divisible by exactly the first power. All right? And same for that one and same for that one. So the difference of any two is divisible exactly by the first power. And that means that they couldn't both be divisible by the second power, because then the difference would also be divisible by the second power. Okay, is that an answer? Okay. So we have these three. C plus eta bears the major burden, and it's equal to this power of lambda times some number which is not divisible by lambda. This is divisible exactly by lambda, so kappa 2 is a number which is not divisible by lambda, and this is the same thing. All right. Now we have to digress, and this digression is for a technical reason. Remember what we're trying to do. We have to remember we have one equation, which is this equation, an equation of a certain type with a certain n, and we want to arrive at a similar equation for three different numbers with one lower, with n replaced by n minus 1. So that's what we're trying to do. So we have to find three new numbers. And you can guess that this kappa 1 and kappa 2 and kappa 3 might very well be those three new numbers. But in order for them to correspond to all our conditions, we want them to be relatively prime. So we have to verify that these three numbers are relatively prime to each other. So this is another careful argument. So what we do is I take this, subtract it from that, that's this side, and then it's equal to this minus that, and the x's disappear, and then I get alpha, I get an eta, and alpha minus alpha squared, and alpha minus alpha squared is alpha times 1 minus alpha, so it's alpha lambda eta. So I mean, before I make the second calculation, let me see what the conclusion is. This number is equal to that. This number is equal to that. I can cancel the lambda, and that means I have this. Well, there's an error in the notes, and this. And eta, alpha is a unit, and eta and xi don't have any prime divisor in common. So these two, this number and this number, have no prime divisors in common, and this should be used. Those of you who are familiar with tech will know all those errors are coming from. Those of you who aren't familiar with tech won't know where they're coming from. So there are no common divisor on the right. That means there's no number that can divide both kappa 2 and kappa 3. Otherwise, it would divide this difference, and it would divide that difference. So what we do is we play with these two. We take the difference of this and this, and we do something similar with this and this too, except now we want to get, before we wanted to arrange things so that when we took the difference, the xi would be removed. Now we arrange things so that when we take the difference, we multiply this by alpha. We have alpha cubed eta, which is eta. This by alpha squared, which gives us alpha cubed eta, which is again eta. So we do it in another way, and we arrange that the etas are canceled from the difference, and we again get a multiple of xi. So that's this relation. So with that kind of argument, we established that kappa 2 and kappa 3 have no divisor in common. And then we can do same thing, something similar for kappa 3 and kappa 1. Just we could do it well or we can do it ill. I did it ill, but so I won't try to do it. So I just arrange. I take the equations involving kappa 3 and kappa 1, and I subtract. I take a certain appropriate multiple of one, appropriate multiple of the other, and I take the difference so that the c disappears. I don't take any multiple, in fact, and the c will disappear, and I look carefully and see what's left. I hope the second time I look more carefully than the first, and it's minus alpha squared lambda eta. And then I arrange to take appropriate multiples with alpha squared so that the eta disappears, and then I get c. So the same argument as before, canceling the lambda shows that now kappa 1 and kappa 3 have no divisor in common. And a third calculation of the same type shows that kappa 1 and kappa 2. So we now have these three numbers that we substitute. Now, so we have these three numbers, these three values for these, and we substitute that in this equation. And what do we get? We don't get that. You see, I don't know how I managed that. What do we get? We want to substitute, oh, I see, this value and this value and this value in here. We have lambda 3m minus 2 and a lambda and lambda, which altogether give a lambda to the 3n. So that would go away, lambda to 3m, and we'd be left with kappa 1, kappa 2, kappa 3 here. But on the the error, it seems to me, is there, right? So that error corrected, we have this. All right. Now we have to use prime factorization strongly. So here we come to this point, to the core of the argument. Understand? And you'll see, at least to some extent, how Kummer has to change this particular argument later, when we begin to have ideal numbers. So we have here minus epsilon, which is a unit, then a number which is a third power. That means we think of how this number on the left factors. We're going to take the prime factorization of gamma, then we're going to take every prime power that occurs there and raise it to the third power. So every prime, on the left-hand side, every prime occurs to a power that's 3 times something. Now on the right side, any prime factor of kappa 1 is not a prime factor of kappa 2 and kappa 3. That means if we take a prime factor of kappa 1, it has to, in order to match, be something to the third power. So if we took a prime factor of pi 1, it has to appear in kappa 1 to the third power. Take a second factor of kappa 1, has to appear to a third power. So kappa 1, we think of its prime factorization, has to have all the primes appearing to third powers and then a unit. So we're using this properties of this prime factorization very strongly. That means that kappa 1 is almost a cube. In other words, we can't do much about the unit, these units that get in the way in this domain z of alpha, but the rest is a third power. And theta, we get it just by taking each of these primes and removing the 3. We raise pi 1 to the a1, pi 2 to the a2, and so on. So there we are. There's kappa 1. And for the same reason, we could do exactly the same thing with kappa 2 and some different primes. We don't have the same primes in kappa 2 as in kappa 1. We could give an example, except, of course, there are no examples since we're trying to show that. This is impossible, so there's no question of illustration. So kappa 2 is a unit times the third power, and kappa 3 is a unit times the third power. So we know that, and then we substitute it in here. We now know more, and we replace kappa 1 by theta. So we have theta, phi, and xi. Now, one more calculation that just comes out of the air, out of thin air. So 1 plus alpha squared is 0. That's all right. So we just expand this. So we have 1 times xi plus eta, and then we have alpha times xi, and alpha times alpha eta is alpha squared eta, so you put that here. Then we have alpha squared xi, and alpha squared is alpha, so this is alpha eta, and there's alpha eta. So there we are. So you see that one has to think a lot to arrive at this equation. It's not surprising, for example, that this is not the way Euler did it. So we have this. Xi plus eta, that's a unit times lambda to the 3m minus 2 theta. Alpha, xi plus eta, alpha eta is a unit times lambda phi cubed, so epsilon 2 alpha. So we have this equation, all right? So from which we can cancel lambda. And that's equal to 0. Cancel the lambda. So it's 3m minus 3. And then if we want, we can simplify it even a little further. We can divide through by the coefficient of, say, phi, by epsilon 2 alpha, in order to just have phi cubed left. So we make that division. We see what we have for the coefficient of xi. We have a unit and a unit. Now remember what the statement was. The statement, what we want to show was that if we had an equation like this with a given power here, we had a similar equation satisfying all the auxiliary conditions, but with n replaced by n minus 1. We've almost done it. We start off with n equal m, and now we're down to n equals m minus 1. The only difficulty is that at this stage we have, instead of just the 1 unit that we wanted, we have 2. So we have a problem there, right? We haven't shown yet that we managed from a solution of this equation with n equals m to arrive at a solution of a similar equation with a different 3 numbers, with these 3 numbers, phi, xi, and theta, instead of xi, eta, and gamma. But we've almost done it. So all we have to do is try to get rid of this nasty epsilon to the 4th. If epsilon to the 4th is a unit, if it were minus 1, that would be no problem. We'd just replace xi by minus xi. But if it were alpha or alpha squared, we're in trouble. We can't get rid of it so easily. All right, so let's finish. The number m we had shown had to be we suppose it was at least 2, in fact. So this is at least lambda cubed, because m is at least 2, so 6 minus 3. So this plus this is divisible not indeed by lambda cubed. So what does that mean? Neither of those numbers are divisible by lambda. We saw that. We should have seen it. And so that means that their cubes are equal to, except for a multiple, in fact, of lambda to the 4th plus or minus 1. So this number, up to a multiple of lambda to the fourth, and therefore certainly up to a multiple of lambda squared, is plus or minus 1. This c cubed is plus or minus 1. So what up to a multiple of lambda squared? So up to a multiple of lambda squared, we have this relation. So now this one last little calculation, so it's a kind of a miracle. So we look at those 6 choices. We just have seen that if epsilon to the fourth is plus or minus 1, we can remove it. So let's forget that. Let's see if this is possible for, if we can have, with this number being plus or minus alpha, if we could have such a relation. So I look at all the possibilities. If this number, if you have a plus here and a plus here and alpha, then I have 1 plus alpha. This is you can see that this is square. 1 plus alpha is minus alpha squared. So computer fatigue of some sort it must have set in. So if epsilon fourth was going to, this would be plus 1, and this was plus alpha, then I discovered that this left side is would be minus alpha squared. But minus alpha squared is not divisible by lambda squared. If I had minus 1 and minus alpha, then I have plus alpha squared. That's not divisible by lambda squared. If, on the other hand, I had plus 1 here and epsilon to the fourth, and I had a minus alpha here, it would be plus or minus 1 times 1 minus alpha, and that would be lambda. But lambda is not divisible by lambda squared. And for the same reason, I couldn't have epsilon to the fourth being plus or minus alpha squared, because then I would discover that either this number or this number was divisible by lambda squared, and this is a unit, and this is divisible exactly by lambda. So what we discover is that epsilon to the fourth has to be plus or minus 1, and so we can we can suppress it here because we just changed c. So that's the complete argument, right? We show that in assuming that we have a solution of the equation for n equals 3, and even this more general equation with the numbers in this domain z of alpha, we arrive at a contradiction. So that's, so to speak, the hardest argument we've had this year, you'll be happy to know. And I stopped to ask if there are any, once again, if there are any questions or any comments from the more sophisticated members of the audience. No? All right. In that case, then, I would guess we'd best stop here. In other words, we could go on. We could probably even do the second part of the argument very quickly, but I think that would be ill-advised. So I would like to do the unique factorization next time, which is an easier argument. It's a nice, if you look, it's an argument done pictorially, and it's just as in Euclid, right? It's Euclid's argument, but with these new more numbers. And after that, my inclination is to coast. There'll be one lecture in which, so to speak, I indulge you. You will see that I probably would have been happier and maybe even better as a history teacher, and better, unlikely, but I might have been happier as a history teacher in a small liberal arts college. So, and then we'll just try to say a little about what Galois theory is, and we'll just try to say a little about how Kummer takes this argument and makes it work, not in general, of course, as you know, but much more generally. And that should take us, I guess, the next 3 lectures. Thank you for your patience, and if you have any questions, send them to me.